We're now ready to derive a confidence interval formula for the population mean. Let's go back and review our general formula for a confidence interval. It says you should start with a point estimate and add or subtract a margin of error. The population mean is mu, and if we're trying to guess it, the point estimate for mu is x bar. The population standard error is sigma over root n, and if we're trying to guess it, the best guess is the sample standard error, s over root n. And then lastly, when we're looking up a t-value, we need to use t sub alpha over 2 of n minus 1. Putting this together, we can say that the point estimate for our confidence interval is x bar, and the margin of error for our confidence interval is t sub alpha over 2 with n minus 1 degrees of freedom times that standard error, s over the square root of n. Let's talk about this formula in a little more detail. This is true under the assumptions that if you have a large population, the data come from a simple random sample or a randomized experiment. Now, to decide that the sample size is large compared to the population, what you'll do is take your sample size, little n, and divide by your population size, capital N. And if this value is 0.05 or larger, then you have a large sample size. It's basically saying you sampled 5% of the population. Now, if you sample less than 5% of the population, if this division comes back less than 0.05, then you now have a second assumption to meet. You still need to have your data from a simple random sample or a randomized experiment. But additionally, your data will have to come from an originally normal distribution. And the way we checked this was a dot plot, a histogram, a box plot, and a normal probability plot. We said dot plots weren't a very accurate method to use. We said histograms were fine for large samples, that's case 1, but they're not very accurate for small samples, which is case 2. And we only need to check for normality in case 2, small samples. So this method won't work, which leaves us with the box plot and the normal probability plot. And this is what you'll use to check the assumptions. Let's just practice working with these assumptions for a minute. A simple random sample of size n is drawn from a population of size 45,000. If the sample size is 12, what conditions must be satisfied to compute the confidence interval? We need to figure out if we sample 12 people, that's equivalent to what percent of the population being sampled. So we'll divide these two numbers, sample size divided by population size. This is 2.67 e negative 4, which is scientific notation for 2.67 times 10 to the negative 4th power, which basically means move your decimal 4 places to the left. This is clearly less than 0.05, the number you need to check. So we know that our sample size is less than 5% of the population. When we sample less than 5%, we need simple random sampling, and we need our data to come from an originally normal population. So here I've said we need simple random sampling, and we need the data to come from an originally normal population, which we would check by forming a box plot or normal probability plot. Now let's say that instead of sampling 12 out of the population, we sampled 2,500 people out of the population. This is 0.056, which is greater than 0.05. So we need to sample 5% of the population at minimum, and we sampled 5.6% of the population. When we sample more than 5% of the population, the only assumption we need to satisfy is that the data came from a simple random sample. To form a confidence interval for the population mean, does the population that the sample is drawn from always have to be approximately normal? The answer here is no. Your data only has to be normal if your sample size is small. Your data does not have to be normal if the sample size is large. So we'll say for a large sample size, your data does not have to come from a normal distribution. Let's practice forming confidence intervals now. U.S. fire departments responded to an estimated average of 157,300 home structure fires involving cooking equipment per year. These fires caused an annual average of 380 civilian deaths, 4,920 civilian injuries, and $794 million in direct property damage. National estimates of reported fires were derived from the U.S. Fire Administration's National Fire Incident Reporting System. By the way, in the future you may see me refer to this as NFIRS. And NFPA's Annual Fire Department Experience Survey. Here I've included a bar chart that shows home fires involving cooking equipment that began with cooking materials, including food by type of material first ignited. If you look, there's food and starch, excluding fat and grease, and then there's cooking oil or other combustible liquid, and then fat, grease, butter, margarine, or lard. And it's kind of broken down by the percent that resulted in fires, civilian deaths, civilian injuries, and direct property damage. So let us say that the National Fire Protection Association randomly sampled 1,000 counties. So right away we know that our sample size N is 1,000. Throughout the United States, and found that the U.S. fire departments responded to an estimated average. So we know that this is X bar. So they responded to an estimated average of 157,300 home structure fires involving cooking equipment per year, with a standard deviation, S, of 3,500 homes. Based on this information, I would like us to construct a 95% confidence interval for mu. And mu here is the mean number of times that the U.S. Fire Department responded to home structure fires involving cooking equipment. When it says 95% confidence, that tells us that alpha is 0.05. Here's your confidence interval formula. Let's plug in our numbers. X bar is 157,300. From here, we will add and subtract a t-value with an alpha of 0.05 divided by 2 and n 1,000 minus 1 degrees of freedom times the standard deviation divided by the square root of n. We need to go to the table to look up this t-value that we'll use in our confidence interval. This was the t-value we're looking for, t.05 over 2, which is 0.025. If you're looking for 1,000 degrees of freedom, you'll go to degree of freedom and drop down to 1,000. This lines up to give a t-value of 1.962. So we now know that this number is 1.962. The lower bound is 157,300 minus 1.962 times 3,500 divided by the square root of 1,000. This puts the lower bound at 157,082.8. To get the upper bound, you should now do the plus. That gives back 157,517.2. I've copied our confidence interval formula to this page so that we have room to write out our interpretation. You should start by reporting your level of confidence. So you're basically saying that you're 95% confident that the average is somewhere between 157,082.8 fires and 157,517.2 fires in a one-year period. Now saying mu is pretty vague. So instead of mu, let's go back and get the words for what mu represented. Mu represents the mean number of times that U.S. fire departments responded to home structure fires involving cooking equipment. So we'll take this sentence and plug it into our interpretation. We are 95% confident that the mean number of times U.S. fire departments responded to home fires involving cooking equipment is somewhere between this lower bound and the upper bound. Now let's say I change our confidence level. Instead of forming a 95% confidence interval, I would like us to form a 99% confidence interval. And we know the alpha that goes with 99% confidence is 0.01. I'm going to grab this general confidence interval that we set up right here and just change the alpha value that we plugged in. So here's the confidence interval formula from the previous page. And the only thing that I'm changing is the alpha. It's now 0.01 instead of 0.05. We're now ready to go to the table and look up this t-value. 0.01 divided by 2 is 0.005. Usually once you know the alpha over 2 is one column to the right. So here we're looking for tail area 0.005 with the degree of freedom 999. However, in the degree of freedom column, 999 doesn't appear. The closest value is 1,000, so we'll just use that. And this is 2.581. Let's go back and plug this in our formula. We're now ready to get the lower bound and upper bound of our confidence interval. This is the resulting confidence interval. In the first confidence interval we formed, our level of confidence was 95%. In the second confidence interval, our level of confidence was 99%. And I want to know what happened to the margin of error between these two confidence intervals. Let's go back to each confidence interval, and I'm going to circle the margin of error and then write it down again on this page so that we can compare them. For the 95% confidence interval, the margin of error is everything after the plus minus. So this entire portion represents the margin of error. So the margin of error for the 95% confidence interval was 1.962 times 3,500 over the square root of n. Now we know that S stayed constant, and we know the sample size stayed constant. The only thing that changed was our t-value for the 99% confidence interval. Here's our 99% confidence interval, and the margin of error comes from everything after the plus minus. So 2.581 was the new t-value. So you could say this margin of error is about 217, and this margin of error is about 285. The way these work in your confidence interval is you always start at your point estimate, which is x bar. So in our confidence interval, we started with an estimated average of 157,300 home structure fires involving cooking equipment within a year. Now, if we want to be 95% confident, to this value you add 217 and you subtract 217. 99% confidence says that you should add 285 and subtract 285, just to give you a higher level of confidence. So coming up here to the question, it says, what happened to the margin of error, and what did this do to the confidence interval? Overall, we can say increasing the sample size increases the margin of error, forcing the confidence interval to get wider. This is a good bit of theory to be comfortable with. As you increase your confidence from 90 to 95 to 99, the confidence interval will get wider and wider. Gives you a greater chance of capturing that population mean. Let us say that the National Fire Protection Association had instead randomly sampled 3,000 counties instead of 1,000 throughout the United States. But they still found the same mean, same standard deviation. So here's our general confidence interval formula. We know the mean and standard deviation are the same. So I went ahead and plugged in the mean for x bar and the standard deviation for S. Now, the things that have changed, it says we've now sampled 3,000 counties, that's N. So in our t-value, we're looking for 3,000 minus 1, that's 2,999 degrees of freedom. And the alpha goes with the 95% confidence, so alpha here is 0.05. We need to take that number and divide it by 2. The only thing left to find here is the t-value that we should plug in. 0.05, right here, alpha, divided by 2, which would be the next column to the right, gives back a tail area of 0.025. Now if you come to the degrees of freedom and look for 2,999, you won't find it. Basically, they've said jump to the z-curve, leave the t-distribution, jump to the z. And this gives back 1.96. Alright, we're now ready to get the lower bound and upper bound of our confidence interval. The lower bound of our confidence interval is 157,174.8 fires, and the upper end is 157,425.2 fires. I now want to know what happens to the margin of error when the sample size increases. In our first sampling, n equaled 1,000, and in our second sampling, n equaled 3,000. And we formed a 95% confidence interval. So we need to go and look at the 95% confidence interval with 1,000 and get a margin of error. Coming back a few pages, here's the n of 1,000, here's the 95% confidence interval, and we already circled up the margin of error. It was right here. So let's just go ahead and record that again. So the margin of error was 1.962 times 3,500 over the square root of 1,000, which is approximately 217. Now let's go get the margin of error for sample size 3,000. Here's sample size 3,000, 95% confidence. The margin of error is everything after the plus and minus. So this margin of error is 1.96 times 3,500 over the square root of 3,000, which is about 125. So as the sample size n increases, the margin of error did what? Decreased, and went from 1,000 to 3,000. The margin of error went from 217 to 125. Just to help you visualize this, let's put it on a number line. To form that confidence interval, you start at your point estimate, x bar. And when n was 1,000, you added 217 and you subtracted 217, the margin of error. But when you jumped your sample size up to 3,000, you only had to add 125 and subtract 125. But both of these still gave 95% confidence. So when you have the larger sample size, you're able to be more accurate, narrow interval, but with the same strength of confidence. Here are the works cited used in this lecture.